This video is on one-slit diffraction. Question 1. Define diffraction. Give 2 examples. Diffraction is the spreading of waves around an object. So for example, sound waves spread or diffract so people can hear others if they are in another room. Example 2. Light waves spread or diffract through a small slit. Important, do not describe diffraction as the bending of waves around an object. So we're going to use the word spreading, yes, not bending. Question 2. Draw the lab setup in the intensity versus distance graph for single slit diffraction. So here we have a laser on the left. It emits monochromatic light, meaning one wavelength. We could see the wavelengths, and then we could see the single slit. Then we could see the diffraction of the light which passes that single slit. And then we see this pattern. We got the central maxima in the middle. And then we got destructive interference, then constructive interference, then destructive interference, and constructive interference, and on and on. So areas of constructive interference, we call that maxima. Areas of destructive interference, we call that minima. Question 3, derive the equation theta equals lambda over b. So this is an equation which tells us destructive interference for single slits. So the previous video had an equation for constructive interference for a double slit. This is destructive interference for a single slit. Okay, so check this out. This line AP and BP are parallel to each other almost if the distance between the screen and the slit, big D, is big. So this is not a good image, but this is better. This horizontal distance between the slit, single slit, and the screen is much longer than this vertical slit width. So we could take these two purple lines to be parallel towards each other. Okay. And this little red line is the path difference. And this is the slit width B here. Okay, so recall for destructive interference from a few videos ago, we have this equation. The path difference is n lambda over 2. So if we let n equal 1, we're going to get lambda over 2 on the right side. And this length here, this red length, is b over 2 times sine of theta. Now we know sine of theta is about theta for small angles. So now we have b theta over 2 equals lambda over 2. So solving for lambda, for small theta in the first minima, we get theta equals lambda over b. And the thickness of the central maximum is 2 theta, which is 2 lambda over b. What does that mean? That means in this image here, the thickness of the central maxima from one minimum to another minimum is 2 theta. Which is also 2 lambda over b. So theta is the angle between the central maximum and the first minimum, units of radians. Lambda has units of wavelengths, lambda has units of meters, and b has units of meters. So you could see the units on the left side equals the units on the right side, no units. Question 4, what will happen to the thickness of the central maximum if the wavelength of a wave passing through a single slit is increased? Well, if theta increases, then 2 theta increases. What if lambda decreases? Well, if lambda increases, then 2 theta increases. Part B, if lambda decreases, then 2 theta decreases. And what will happen to the thickness of the central maximum if the opening of a slit is increased? Well, you could see if B gets bigger, then 2 theta gets smaller. Finally, if B is decreased, then 2 theta increases. Question 5. What happens when white light passes through a single slit? Recall Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. Indigo, violet means purple. So we see a pattern like this. We get white in the middle, then we get Roy G. Biv outside of it. Question 6. Play with the following simulation. Draw and record what you learned. So go on this website and first bullet, describe the interference pattern as the wavelength increases. So start increasing the wavelength. What happens to the distance between the two maximums? And then describe the interference pattern as a slit width increases. So you can see we have another option, slit width. What happens to the distance between the maximums? Okay. Question 7. A monochromatic light source with a wavelength of 5,500 angstroms is shined through a single slit onto a screen placed 75 centimeters from the slit. The distance between the center of the central antinode, meaning central maximum, and the first node, the first minimum, is measured to be 1.10 millimeters. What is the width of the single slit? So let's just use this equation. And we get this solution. Part B, how far from the center of the central antinode, central maximum, will the first order node, fourth minimum, be found? So we're going to use this equation here. Part C, how far from the center of the central antinode, central maximum, will the second order antinode, second minimum, maximum be found? So we need to use this equation here.